if all population growth could be explained by exponential growth, then the planet would be completely covered with whatever organism is or whatever population is experiencing exponential growth. But the planet's not covered with elephants or bacteria or dogs or cats. So exponential growth cannot explain population growth fully. That J-shaped curve only exists, remember, under ideal conditions. That means plenty of food, plenty of shelter, no predators, no waste accumulating. So it can occur over a short time. Bacteria are a good example. If you put bacteria in a petri dish with a petri dish is a little plastic dish with nutrients inside it, so more nutrients than the bacteria need, they will experience exponential growth. But eventually that growth will slow down because the waste will accumulate and they'll run out of room. So that's where we get to what really happens with populations, which is shown by this S-shaped curve. This S-shaped curve represents what's called logistic growth. So those two terms really need to go in your notes. Exponential growth, logistic growth. And you need to explain them to yourself fully so that you can recognize them when you see them and figure out when they occur. Logistic growth occurs when a population's growth slows. You can see it slowing. So notice that we start out with exponential growth here, right? We see it slow and then fast, but then that growth slows and then stops. So here we have essentially zero population growth. It's actually up and down and up and down and up and down, but it goes up and down along this dotted line that's labeled carrying capacity. Logistic growth occurs when a population's growth slows and then stops following a period of exponential growth. So exponential growth becomes logistic growth. Many familiar plant and animal populations follow a logistic growth curve. Logistic growth is when population growth slows and stops following a period of exponential growth. Something has to happen to keep a population from growing exponentially forever. Population growth in real-world populations is logistic growth. This kind of growth shows three distinct phases. The first phase is phase one. And phase one is, you can see that J-shaped curve, phase one is logistic growth. Or I'm sorry, phase one is exponential growth. So a new population starts growing exponentially, but then after a short time, the resources are limited. We start finding out that organisms can't grow exponentially for long periods of time. The resources during phase one are more than the population needs. Few individuals die and many offspring are produced, so both the population size and the rate of growth increase more and more rapidly. In phase two, the population is still growing, but it's growing more slowly. So in phase two, the growth slows down. In real-world populations, exponential growth does not continue for very long at all. At some point, the rate of population growth begins to slow down. This doesn't mean that the population size decreases. The population still grows, but the rate of growth slows down, so the population size increases more slowly. And then in phase three, the growth stops. At some point, the rate of population growth drops to zero. This means that the size of the population levels off and it stays stable. Under some conditions, the population will remain at or near this size indefinitely. This is what we call an S-shaped curve versus the J-shaped curve of exponential growth. So the population grows most rapidly during phase one. It starts to slow down. The growth slows down in phase two, and then it stabilizes in phase three. It doesn't mean we don't see a straight line here, because there are going to be changes, like maybe predators move in, and then the population decreases, or a disease causes the population to decrease. But then after the population decreases, there are going to be more resources, and so then maybe the next year we'll see an increase in the population. The population grows when more organisms are born or added to it. Then there are organisms that die or leave it. So population growth may slow for several reasons. Growth may slow because the birth rate decreases. It may also slow if the death rate increases or if births fall and deaths rise. Population growth may also slow if the rate of immigration decreases, the rate of emigration increases, or both. When we reach this point at which the population stays stable, we see that it's called carrying capacity. And we'll talk about carrying capacity in a minute, but I want to address one misconception, or a few misconceptions. First of all, don't forget if you were drawing a graph of population of logistic growth, sometimes people want to leave out phase 2, that gradual change in the population growth. So sometimes when people are drawing their S-shaped curves, they show the exponential growth and then a sharp leveling out. It's not a sharp leveling out, it's gradual. Also remember, and notice on this graph, the population doesn't start at 0. Okay, it's above 0, and if you were drawing a graph of any kind of population growth, of course you're going to start higher than 0, because you can't start a population from nothing. So there has to be, at least in an organism that reproduces asexually, there has to be at least one individual, and if they reproduce sexually, then there has to be at least 2 of them. I said we would talk about carrying capacity soon, and here it is. Carrying capacity is always included in logistic growth because carrying capacity is the size of the population that can be supported in any one environment. So when the birth rate and the death rate are roughly equal, or in immigration and emigration are roughly equal, or more accurately, if the birth rate plus the immigration rate is equal to the death rate plus the emigration rate, then the population growth stops, stays at 0. Population might still rise and fall somewhat, and we see that here. The population continues to rise and fall here, but the average population stays the same. The ups and downs average out around a certain population size. If we look at this dashed line, we see again it is carrying capacity. This is, so if we look and see where this line intersects the y-axis right here, that should show a number of individuals that represents the carrying capacity. That's the maximum number of individuals of a particular species that an environment can support. So different environments are able to support different size populations. So each environment has a specific carrying capacity for a specific population. And that depends on both biotic and abiotic external factors that affect the population in ways that stabilize it at that size. There's only so much space, so much food, and so only so many individuals can be supported in an area. Again, so carrying capacity is an important concept added to your notes. That's the maximum number of individuals of a particular species that a particular environment can support.